Here you will be getting this. Yeah, this. Yeah, now it is tuned. Okay, you are getting everything. So here. Connect it on the back side. Just hold this second. If this is in white, it will not get locked. And then you rotate this. So rotate this.
Okay. Can we turn it off or?
No, just share this link and post it in that Canvas discussion.
So, question. There's normally an HDMI. Did somebody take it? I have no idea about it.
I'm not too worried about that. But it's like not very. I think I got that's why it's you have to like derive
Can log in your dashboard to. I have already copied the name.
I'll just open my laptop and we'll post it. That's not an issue. Just a second.
Okay.
We have to change this. You just check if the height is okay or something. Is that okay? Okay. Or just a second. Is this okay? Yes. But is this from something?
It's ready to go, or you're still working on it?
I think we can do it in
All right, I think we'll get started. Good to see everybody. Any questions before we get started today? Okay. All right. Well, we'll get going. So, where have we been so far? Well, we've been talking about classification and how you would set things up if you wanted to take a parameterized model and score its ability to do your task, your classification task, and here we've been using a really simplified. We've used the example of a very simplified score function, just a linear function, and we've talked about the how we set up the optimization. So we talked about losses and how we want to use them to indicate how well we're doing the task, and we talked about how we think about loss over our entire data set. We talked about regularization. We talked about loss surfaces and how they can be really complex, and they will be with neural networks as our parameterized models. We talked about gradient descent and how this simple optimization algorithm will be like the basis of a lot of the optimization that we will do with neural networks. We talked about how there's some pretty major costs associated with gradient descent and how we overcome one of those with what's called stochastic gradient descent, where we take random samples of our data, which we call mini batches, and we estimate the gradient of the full loss with the gradient of this loss calculated only on that subset of the data. And somehow that all works great. Okay, so we started on this topic at the end of last lecture, backpropagation, which is the algorithm for how we will compute the gradients of the loss with respect to all the parameters in our model. And we talked about computation graphs, and here's a node in a computation graph that has two inputs, x and y. F is the operation, and z is the output from it. And these could be of different dimensions, and depending on what f takes as input and what it and what it gives as output. You'll recall some of this from the last time, but a bit more in detail. What we do here, what we do in backpropagation, in each one of these, each one of the nodes, which is our operations, is we calculate the gradient local to this operation. So if this is the output, we want to calculate the gradient of the output with respect to the different inputs. So in this case, where we have an x and a y, we have partial z, partial x, partial z, partial y. Okay, so these are our local gradients. The local, again, meaning just local to this operation. This is just one node in a very, possibly large computation graph. And remember, what we're trying to do here is with the algorithm backpropagation, is we're trying to compute the gradient of the loss with respect to our different parameters. And so the loss, this is just one node in the computation graph for the loss. The loss is somewhere downstream, and it's called backpropagation because the way this works is that we start at the loss, at the last operation in computing the loss, and we're going to work our way backwards to the inputs essentially. And so we're keeping track of the gradient of the loss with respect to these different operations. And so the way this algorithm works is that at this operation we already have an expression for the gradient of the loss with respect to the output of this operation. And now we want to propagate that back to these inputs x and y. And we do that by the chain rule, because we think of this as like a composition of all these operations. And so we use the chain rule, and we have simply that the gradient of the loss with respect to this input x is just the gradient of the loss with respect to this downstream gradient here with respect to z, times the gradient, this local gradient here with respect to x. Okay, and now we have an expression for the gradient of the loss with respect to x. And we can do the same thing for y. And then that now will propagate back to whatever operation the x is an output of, or the y is an output of. And we'll just keep going back until we've worked our way through the entire computation graph and have all of the partial derivatives of our loss with respect to our parameters. And then that's what we will use to update our weights, right? Because the idea is, remember, we're trying to minimize loss in general. And so the gradient of the loss with respect to, say, x is telling us the direction of greatest increase of the loss with respect to changes in the input x. And then we use the negative of that gradient to point us in the direction of the greatest decrease of the loss. And same thing for all the other parameters or all the other inputs. Okay, this is the algorithm. And what we'll do today, just pass it back to other operations. What we'll do today is go through some more examples in more detail so that you get the idea and this starts to solidify a bit. So we use fairly simple operations with simple functions with simple operations along the way in the computation graph. And here's one of those examples. So what you see here, there's our function. Notice that it's a function of w and x. So w is our parameters for this function. You can see that w is a vector of 3 values, w0, w1, w2. And then you have an input, x, and x is two-dimensional, x0 and x1. And that's how they all go together in this function here. You can think of this argument for e to the the minus whatever that is as a dot product between the vector w and the vector x, where you've added one more value to x of 1 to make it a 3-dimensional vector, and that's how you get this w2 times 1. So you think of it as like a dot product between w and x, where we've extended x to have one more dimension, and we've set that value to 1 to give you that. And that's kind of a common setup here, where one of your parameters gives you like a bias term, that w2 here. Okay, so let's think about this. Let's break this up into its different operations, its simple operations. And so if we look at this, we have a dot product first between w and x. And you can think of this right here, this whole subgraph of the computation graph as being that dot product. So you have w naught times x naught here, w1 times x1 here, w2 times 1, or just w2. And then those are all added together. We add these two together, we add these two together. And this output here is our dot product. Then that dot product, we negate it. We multiply by -1. So that's what that operation is here. Then we exponentiate it. So we have this operation of exponentiating. Then we add to that 1. Okay, now we have the full denominator, right? And then we have one last operation where we actually make that the denominator 1 over that. So that's what this variable here is showing, is that this is the function 1 over whatever the input is. And then we finally get our output, right? So we've broken this up into kind of simple operations along the way. You could argue that maybe this isn't such a simple operation, exponentiating. When we implement that in code, we often will use truncated series or something like that. So maybe there's something more complicated going on there, but whatever. We'll just be treating that as a single operation of exponentiation. Furthermore, what this has done, this example, is that we've picked values for the parameters w and the input x. And that's what those green numbers on the far left over there. So w0's 2, w1 is -3, w2 is -3, x0 is -1, x1 is -2. Okay? And then we do what's often called a forward pass in, like in computation, is that we take those inputs and we run it through the computation graph. So we run those things from inputs forward to the outputs. So that's often called the forward pass. And we just do all the operations, right? So 2 times -1 is -2, -3 times -2 is 6. We add -2 and 6 together and get 4. We add 4 and -3 together and we get 1. Multiply by -1, we get -1. We exponentiate that, we get 0.37. We add to that 1, we get 1.37, and we compute the reciprocal of that, 1 over, and we get a 0.73. Of course, this is, there's obviously more, like you could have greater precision here, have more numbers here behind the decimal point, but this is just for, to illustrate, we just have a couple of couple of points of precision. Okay, makes sense, kind of what the setup is so far? All right, so we're gonna do back propagation here. We're gonna compute the gradient of the loss. Where the loss here is just so the example here is maybe not a loss, just a function f. We're going to compute the gradient of f with respect to eventually our parameters. What we want to do is, we want to compute. We want to know how the function changes with respect to our parameters at this data point. But importantly, one thing to understand about this algorithm is that we're not computing necessarily like the full gradient here for any values w and x. This algorithm is for a fixed choice of the inputs to f. So our parameters w and then our data input x. Right. So we're computing the gradient of f with respect to basically anything in this graph, but in particular with respect to the w's and x's at those values of w and x. Okay. So it's like a particular data point and a particular set of weights. Does that make sense why I'm making that distinction? Yeah.
Would the data points be from our training set?
Yeah, in general these would be from your training set, yeah. If we're doing learning, we want to only learn on our training set. Yeah.
Quick question.
Yeah.
So when we compute the gradients for W, that makes sense to me because that's what we're looking to change, but I'm a little confused on why we are thinking about our x's because those are just our data. We can't change those values, right?
Yeah. So yeah, in general in general you could think of all those just as inputs to f, and you could ask how does the output change with respect to the inputs. You're right that the way we framed all of this for optimizing our model with respect to its parameters, we only care about the gradients with respect to the parameters. And this algorithm will allow us to compute those, as well as compute the gradients with respect to the data point as well. So you can just one kind of answer to the question is that's fine. We just ignore the gradients with respect to the data. We need the full computation graph, and how it depends on the data though, because that's part of the computation, right? So like we're not doing it independent of a data point. We're computing it for that data point. Now, on the other hand, you could think of this as like, so the examples we've looked at so far are images, and like each one of these could be like a pixel of an image, right? It's only 2 pixels, but if you think about this as extending this to some much more, many more x's, and if you look at those gradients of the loss or this function here with respect to those data points, you could ask, well, how how could I change my, like the value of this pixel to like reduce the loss or increase the loss? I mean, you know, you could ask different questions. And this will start to say something about, let's say, like instead of it just being like on the loss, let's say that we think about it with respect to the score for a particular class, right? So the score for each one of those classes is going into the loss function, right? And then we're computing the loss. But you can imagine doing this, like let's say that F was like the score for a particular class or something like that. Then you could actually ask this question where you say, okay, give me the gradient of the class score with respect to a change in this pixel. And you can start to say, okay, well, if I change the pixels in this way, I take a step in this direction that changes the image to say, like, give me a greater, if I do gradient ascent in this case, it give me a greater score. So I have a higher likelihood of being one of these, like being an image that has one of these objects in it. And that starts to give you kind of interesting information. In fact, this is one of your homeworks, and like homework 3, I think. Homework 3, where you look at this and you compute this, and you kind of you make these changes to your images in such a way that you get it to like to give you a different class. And actually, this gets into a whole interesting topic in deep learning in like convolutional neural networks, where you come up with these adversarial examples that to you and I look like they're of like certainly one class, but we can make small imperceptible changes to them and make them actually get classified as another class. And it's kind of a problem for deep learning. It shows some of the brittleness there, and there's a lot of research into how do you make that more robust. It's not really what we're doing in this class, but you'll get some of the kind of taste and flavor of that by doing the homework and some of the lectures that have come up in a couple of weeks on that. And you probably got way more than you bargained for in that answer, but yeah, that's so there's interesting information. TLDR, interesting information in the gradient with respect to the inputs as well. All right. Okay, so what are we going to need here to do this? Oh yeah, we're going to need to think about each one of these operations and what their gradients look like with respect to their inputs. Fortunately, we've chosen some fairly simple ones so that we know we can, analytically we can easily write down what the gradients look like, and we can use those. The local gradients look like, and we can use those for doing this. And then in this case, everything's all one-dimensional, so these are just derivatives, not partial derivatives. But there you go. Okay, so any questions on this? Hopefully, this all just looks like the inside cover of your calculus textbook. All right, so let's start working our way back here. Let's do backpropagation. So backpropagation always starts the same way. We think of this as an output variable. It's whatever name we want to give to this. We don't want to keep using f over and over again. We already used it. Just the output of this is being something like z. So we're asking like, what is the gradient of the output with respect to itself? That's kind of how you seed the backpropagation, or you initialize the backpropagation algorithm. As you compute, you're computing. You need the initial downstream gradient to be used. When we do when we use the chain rule to push downstream gradients upstream. So the first one's always 1, because we're just taking basically the gradient of the output with respect to itself. So we just get a 1. So you always write down a 1 here when you start this thing. Okay? So now what we need to do is we need to compute localized gradients here with respect to the inputs. So we know that the derivative here of 1 over x is minus 1 over x squared. We're going to evaluate that at the value of x, or the value of the input, 1.37. And that will be the gradient, the local gradient here at this node, that number right there. And then we're going to multiply it with respect to, or we're going to multiply it to the downstream gradient, and that'll give us the new downstream gradient that we're going to use as we propagate back upstream. And that happens to be minus 0.53 here, okay? Questions on that? Do you see how that happened? This is the upstream gradient. This is the local gradient. We computed at the values of the, in this case the inputs here. We do all the math here and we get a value of minus 1.53. So this is now like the new downstream gradient that we're going to push upstream. By the way, what is this gradient right here? This is the gradient of what with respect to what? Or the partial derivative of what with respect to what? Yeah, and it's kind of like, it's confusing for me to ask you that because it's a little bit like maybe too obvious in some sense, but it's good to kind of get it solidified. This is the partial derivative of the final output with respect to the output from this node, or what becomes the input to this node, right? Okay, and as we go down, each one of these red numbers we're going to have underneath here is going to be the partial derivative of the final output with respect to the output from that node coming into that branch. As we get to more branches, you're going to have to pay attention there, but we have single branches right here. So again, as we're moving backwards, it's just like it's always partial derivative because we're propagating these gradients back upstream. The partial derivative of this final output with respect to basically the inputs to this operation that we're at the stage that we're at. Good? Questions? Should we go faster? Okay, the next one. So here we're just adding 1. That's pretty simple. This is just a constant with respect to the input, so it's going to give us derivative of 0 for the constant. So we're just left with just the input. Derivative of that with respect to the input is just 1. So no matter what the input is in here, we have a local gradient of 1. So what are we going to do? We're going to take that and multiply it with what? Yeah, the downstream gradient at this point, which is minus 0.53, and 1 times anything is itself, so, or anything is that anything, so we have minus 1.53 again. Good. Next, we have an exponentiation operation, e to the x. One of the nice things about e to the x, its derivative is itself, right? So simple, at least to remember and write down. So what's this going to look like? We have a local derivative of e to the x, and the value of x in this case is minus 1. That's the input. So we're going to have an e to the minus 1. That's going to be the local gradient at the chosen values for the inputs. And we're going to multiply that with what? Minus 0.53 again, because this represents the downstream gradient that we're propagating upstream. So we're going to have an e to the minus 1 times minus 0.53. That gives us roughly minus 0.2. Okay? So now we have minus 0.2. What does this number here represent? Minus 0.2 at this point? It's partial derivative of the final output with respect to the input here to this operation, or the output from this operation. Those are the same thing, right? So we're going to keep doing this until we get all the way back to the parameters, which is what we care about, right? So seems maybe too simple, right? But this is good because simple algorithms are easy to understand, easy to reason about, and this gets the job done. It's very fast, and this is what we use to compute gradients numerically for for gradient descent. Okay, we keep going, multiplying by minus 1. There's our local gradient. If a constant times our input, derivative of that with respect to the input is just that constant. So this is a minus 1. Notice it doesn't depend on the input. So we have a local gradient of minus 1. And we're going to multiply that with minus 0.2. That gives us 0.2. See how we're going? We're just, okay. So now this was kind of, this was simple, I suppose, up to this point, because we only had one operation, one input to each of the nodes as we were going backwards. Now we have 2 inputs. What do we do? Yeah, we just do what we just did here before, but we just do it for both branches. We just keep working our way backwards. Again, because the way that partial derivatives work, the way that like all these compositional rules work, if we're we add the gradients together in these operations. Okay, so let's look at this. We have an addition. Here it's 4 plus minus 3. So let's focus on one of these. I think we're doing the top one. I forget how we do this. Yeah. I'm going to do both at the same time. So we have the gradient. We have the gradient of this plus operation with respect to this input right here. So what does that look like? What's the gradient? 1, yeah. I mean, it's down here. Depending on which point of view you take, if we're thinking about this sum where this is the variable that we're concentrating on, this is a constant with respect to that variable. So it looks like this, but it doesn't really matter. Like in general, this is just a gradient of 1. So we have a local gradient of 1 times the the downstream gradient of 0.2, and that gives us 0.2, and it's just, by symmetric reasoning, just swap the variables there. We get also 0.2 here as well, right? Because this gradient, we just kind of swapped, which one was the variable, which one was the constant as we change between the branches. But regardless, the gradient was always just this constant 1, so they're the same there. Okay? Almost done. So first of all, good news, we've got one gradient of the output with respect to a parameter, 0.2. So we're on our way. That did feel celebratory. I'm glad there's a little bit of music to celebrate in this. Well done. Good timing. All right. This should feel pretty easy now. There's another sum here. So whenever there's sums, there's always just a local gradient of 1. So we just take whatever was the current downstream gradient and we just propagate it up. It's just 1 times that. So we get that number again. So again, those 2 branches, we get a 0.2. And now we have a multiplication to deal with. So multiplication, we've got our formula here for the derivative of the product, a times x. So one of those is going to be our variable, either x or w naught or x naught. And the other one will be our constant. And so when we take the derivative, we with respect to the input, we just get the constant. So if we do this with respect to w naught, what's the local gradient? If we think of w naught as being the variable, what's the local gradient? Not 2. If w naught is just the local gradient, not anything else. Minus 1, right? Because it's x naught times w naught. So if w naught's the variable, we're taking the derivative with respect to that. Then we're left with x naught, so it's a minus 1. So the local gradient going along this branch is going to be minus 1 times 0.2. That'll be a minus 0.2. How about going the other way? The local gradient with respect to x naught will be 2. 2 times 0.2 is 0.4. So we'll get those gradients. And this was like a fun mistake that has always persisted and never fixed it. But it's correct here. 0.4 and minus 0.2. And then, there's not another one there. Let's do this one in our heads though, just to practice. So we move along this branch right here. We think of W1 as being the variable. So we take the local gradient of this operation, this product, with respect to W1 gives us a gradient of -2 times 0.2 will be -0.4. And then the other direction, we go down to x1. The local gradient with respect to x1 is -3 times the 0.2 gives us a -0.6. And that would be gradient there. And then we've computed at these values of our, like all the inputs to the function, we've now computed the gradients with respect to the gradient of the output with respect to those inputs. And granted, for a function as simple as this, you probably could have done it, I mean, faster for you if you just maybe, did a couple of, applied a little bit of the rules of calculus that you know, and worked out what each of these are, and plugged in the values of w and x, and you would have gotten -0.2, 0.4, and so forth. But algorithmically, you can implement this on a computer. It's very fast, and will give you the right answer all the time. Again, no matter how complex this gets.
I was just making sure, because we're treating the x values as fixed, right? So would we calculate the gradients for those?
So again, yes, for the specific application of computing the gradient of the loss with respect to the weights, but we're such expansive thinkers here. We're thinking we may want to also compute the gradient of that, the loss with respect to the data, because then maybe that can tell us something interesting as well. But you're right. Like in general, if we're just doing gradient descent on the parameters, we only care about the ones. So we would say we would not need to compute this one because this would be information we wouldn't use. By the way, this is called the backward pass. So there's a forward pass for this algorithm, right? And this gives you all these values that you need along the way, because you need these, you need these values for most operations to compute your local gradients. So that's your forward pass. And then your backward pass is what is back propagation, is going from our initial value, our initial downstream gradient of 1, working our way upstream. So the forward pass and the backward pass. You hear that a bunch with this algorithm. Okay, questions before we move on? Yeah.
I just had a question. So on the forward pass, are there neural nets that get big enough that storing each forward pass
Yes.
number becomes an issue?
That's a great question. The answer is absolutely yes. So there's different ways that this gets dealt with. One way that is often just made available to you as like a parameter to the optimization that you're running is to write these to disk or to some storage that you have available to you, like to some like network memory or something like that. If you write to disk, you can imagine how that slows things down, because now you're picking up whatever is the cost of the I/O there. But it's common to do that. The other thing that is done is to split these computation graphs up and put them on different GPUs, so that part of this is being done on GPU 1, part of this is being done on GPU 2. It does slow things down again, because now you have to communicate between the GPUs to pass, like at some point to connect up the forward and backward passes. You're going to have communication, but that's perhaps, if this is like really complex and you need to use a lot of GPUs, that kind of communication might be a lot less costly than, say, like writing to disk and reading off of disk. But yeah, there's ways of dealing with that. So yeah, it does matter, and there's also other ways of dealing with this, like what precision you require of each of these operations, right? So like, you might be like single precision, you might be used to that, like a float, having like 32-bit precision or something like that. It's very common in deep neural networks to play with that precision, to do a lot of the operations in floating point 16 rather than floating point 32, again to save half of the memory requirements there. Certain operations that works just fine, no problem. Other operations you tend to need the additional precision to make the learning be beneficial. And there's some like heuristics around that, like each operation. In fact, frameworks like PyTorch sort of take care of this for you, sort of know which ones should be, like, you can sort of select globally to run the whole thing in like floating point 16, but then it will, you know, if you don't force it to do that, it will smartly say, well, batch normalization should be done in floating point 32, so I'll still do that in floating point 32, but everything else will be in floating point 16. We haven't talked about batch normalization, we'll talk about it soon. But yeah, they'll take care of this. So there's like all these different ways for dealing with this thing. So it's a great question. It matters. It's, you know, it's a big deal. It won't matter really for like us and the homework that we'll do, but perhaps for your project, for the final project, and then, you know, in general real life machine learning, you're likely to run into it. Cool, great question. All right. Oh, right. So, you might be thinking to yourself, I could split up this computation graph into a number of different ways. Like I could have, you know, I did this at what, you know, appeared to me to be like the elementary operations, but I could have done this in a different way. For instance, this function here, so sigma of x equal to 1 over 1 plus e to the minus x. This is actually a named function. You might have seen this before, called sigmoid. And it actually has a very simple derivative with respect to its input. If you express it in terms of itself again. So the derivative of the sigmoid is just itself times 1 minus itself, you know, again, at the value of the input. So you might have seen that, you might have known that already, and you might have said, you know what, it's way easier if I just take this whole portion of the computation graph and just say it's a sigmoid function or a sigmoid operation, and this is my derivative, and I'll just use that to compute to do this back propagation algorithm. And that's totally fine, right? The same information is there. You're basically just kind of skipping these steps, right? Like you're doing all of these at once by kind of, you know, compressing all that together into that simple operation. So yes, you can express this at different levels. It will give you the same answer. That's the beauty of math. Yeah. Oh, right. We do this here. So if we were to think of this whole thing as a gate here, or as one operation, and we run this, we have the output of the sigmoid function as being 0.73, the input being 1. So if we apply our algorithm, we have the local gradient with respect to its input is this, and we know that the output is 0.73. That's just like what this is telling us here. So it's itself at the value, so that's 0.73, then times 1 minus itself, 0.73 here, and we get a value of 0.2. We multiply that with the downstream gradient, and that gives us our local gradient here.
So you could take this whole graph and just say,
Yeah.
make that one node.
Right, right. You could absolutely do that. You could compute this. So maybe it makes sense for this because this is still kind of like a fairly atomic like operation that you might reuse over and over and over again. Maybe this one, maybe not so much. You know, you could think about generalizing because like what's one way that this could change like in a fairly straightforward way, but you'd have a very different function would be if you change the dimensions of w and x, right? Like if you extended them, then you have like a different function that you need to keep track of. I mean, in that case, you could imagine how to like write that down, you know, abstractly. But in general, you don't want to try to anticipate like what all these things are. You want to have, you know, like some kind of vocabulary of what all these more or less atomic operations are, know what their gradients are, and then when you write down, like when you program in PyTorch, you know, the automatic differentiation algorithm will just look at that and say, we'll look at how you know, like the composition of operations that you wrote and say, okay, I recognize all those things. I know how to do the back propagation because these are all like in kind of defined units that I can deal with. So yes, you could do that. It's not really to your advantage to do that for every single operation. You do want to think about this as compositions that you can reuse over and over and over again, so that you're not writing down, you know, something like this for every single possible function that you can imagine. Does that make sense? Okay, cool. Yeah, so there's some kind of simple patterns here. So we saw this with addition. Addition, your local gradients are always just 1, right? So whatever is the downstream gradient, it's just going to be 1 times that, so it's going to be itself, and you're just going to kind of move that, you know, through the branches of that addition. So addition in back propagation is kind of easy to deal with. You might think of it as like a gradient distributor. It's just taking this gradient and distributing it across all of its inputs to the addition. Okay. What about for this max gate? So we didn't have one of these in the last one, but this is a max operator. So it takes its inputs and it outputs whatever is largest, right? So if these are the 2 inputs to our max function, 2 and minus 1, 2 is obviously the larger one, so the output will be 2. But what's the gradient of a max operator? And this is kind of fun to think about because you probably don't think about taking gradients of a max operator. In fact, you might have had like a little knee-jerk reaction like, hey, wait a minute, I can't do that. I can't take a derivative of a max function. There's something weird happening at like the point when the 2 are equal to each other. Because like, I don't know, something weird's happening. But it turns out that we take gradients of all kinds of functions like this, and not something that we're going to cover here, but kind of fun to think about if you're interested. Like languages like JAX, frameworks like this really extend this to allow you to take like derivatives of kind of any kind of function you can write in Python, for instance. But anyways, coming back to max, what does the gradient of a max look like? Let's say with respect to z in this case. Z is the larger variable at this moment, so what's the gradient of max with respect to z? One. Because if z is larger than w, the max of z and w is z. So gradient of z, or derivative of z with respect to z is just 1, right? What is it with respect to w? 0, right? Because there's no 0 appearing in that. How about if we switch it around and w is now larger than z? What's the gradient with respect to z? Or the gradient of the max with respect to z? 0, and then with respect to w? 1. Good, good. What happens when z is equal to w?
Both is 1.
That's where mysterious things happen. There's a really good news in general in neural networks is that we have so much precision and there's so much like randomness and stuff that like edge cases like that like never really happen in practice. You can always write something down. In fact, the definitions of these things have something written down because you can't just say like nothing, everything blows up. But in general, like that, like in all practicality, that will never happen or will rarely happen. And you get to decide something reasonable that happens when z is equal to w. Maybe you just say it's equal to z. Maybe you say it's equal to w. They'll give you the same answer when they're equal to each other, but yeah, there's something mysterious mathematical like your calculus 1, self is like, wait, you can't do that. But yeah, you can. It works. So in this case, z is larger. So the local derivative is 1 with respect to z, and the local derivative with respect to w is 0. So we multiply this current downstream gradient with 1, and we get that. This current upstream, or this downstream gradient with 0, and we get 0. So if you were to give this thing a kind of a name, what would you give it? You call this, you know, a distributor. Like, what does this look like? A what?
A one-armed distributor.
A one-armed distributor, yeah. That's clever, yeah. It's like, so, yeah, just 1 second. Just so, one-armed distributor, or maybe a router, routing toward, it just routes the gradient to the largest variable, to the branch with the largest variable, and the rest get a 0. And that's pretty devastating. Think about this. Like, zeros are pretty devastating in back propagation, right? Now you have a downstream gradient of 0, and whatever you do next, you're going to multiply the local gradient with this downstream gradient, and you're always going to get a 0, right? So like, all of a sudden that branch is like kind of dead with respect to gradients, which is fine. But if you think about it, what you're trying to do is you're trying to give signal to how to change your weights to make them, to change your loss. But this max operation here basically said, because this was larger, we're going to just pay attention to whatever's coming in here and not pay attention to anything here. So every other input here to here is going to have a total gradient of 0 because of this. It's just like, it's not, because of this, it's no longer contributing to the loss, or to like the final output here. I'm sorry, there was a question here, then a question there, yeah.
What will happen then that z is equal to delta like this?
Magical things happen there. Write it down, try to graph it, and you come up with the answer you like best. And then you can choose that, and it'll be fine. As long as these kinds of like magical things only happen like in a set of measure 0, we're all good.
So is it possible on this second pass when you come back here and change the weights again that W will be greater than 0?
Yes, absolutely. Yeah, absolutely. For the same data point, or remember, in general, like we have the values of the weights and we put in a different data point. It could be now that this is different, right? So this is just for the particular example that we're looking at. Great question. Yeah. All right. Yeah. So this routes the gradient to the largest variable, the branch with the largest variable. What about multiplication? What does multiplication do? Like kind of switches things up, right? Right? So like, this looks like -4 just multiplied by whatever this downstream gradient is. This looks like 6 this looks like 3 just multiplied by whatever this gradient is. So yeah, it's like a switcher. It's like a scaled switcher. These aren't like technical terms, by the way. It's just kind of like nice to think about what's happening here and give yourself some intuition about. Like, I think this is really important to think about. It's like max operation. Remember, max. We have already seen max show up in the definition of a loss function, right? The SVM loss, or like the hinge loss, right? That has a max operation. So already we're going to be dealing with taking derivatives of max functions. So if you're part of the branch that doesn't give you the largest value here, everything before it no longer contributes to the loss. We're going to see that these kinds of operations are used a lot in very common activation functions, or the nonlinearities. The nonlinear functions we put between our linear layers. We'll come back to things like ReLU, a rectified linear unit, and that is basically a max function as well. Okay, we already sort of mentioned this, but gradients, if you have, if a node has 2 outputs, the question is, what do you do about the gradients that you computed from either branch? They just add together, so they just add together, and then I keep using the words gradient and things like that, which really apply to like higher dimensional things. Usually that's how we talk about them. And it's fine that we talk about them when they're referring to one-dimensional things as kind of like a generalization. And the idea here is to recognize that all of this math, like this whole algorithm, still applies when x and y are multidimensional, z is multidimensional. We just have multidimensional objects here for our gradients, right? These are Hessians, if you think about this in one way, or Jacobians if you think about another, just like whose name gets added to these. But these are derivatives of basically like vector value functions with respect to vector value inputs. And so we get matrices. And again, matrices are just ways of keeping track of all the indices, all the variables of, like all the indices of one variable, and then all the indices of another variable. Right, cool. So let's think about this. Vectorized operations. This will happen a lot. You probably already, if you're doing your homework, which you should already be doing it, if you're doing your homework, you would have already run into this. Vectorized operations are like, in this case, there will be a lot of like element-wise operations, where we'll be applying this max function, say, to each of the inputs of this multidimensional vector. In this case, 4096. This might seem really complicated, but it's like the easiest thing to deal with, right? It's just a whole bunch of one-dimensional operations happening, together. But if it's element-wise, there's no mixing of these, like the entries here, and so these operations become very, very simple. So let's think about this. What is, in this case, this is a way to kind of help you think about these vectorized operations and what kind of objects you're getting when you do these calculations. So this is max being applied to each entry of x, max of that with 0, and when x ends up being of dimension 4096. Okay? Since it's element-wise, the output's also dimension 4096. So what's the size of that Jacobian matrix? The output is 4096, the input is dimension 4096. What's the dimension of the Jacobian matrix?
So does that mean that each output has 4096 derivatives we need to calculate?
Mm-hmm. Right. Yep. Seems like a lot, but actually it's not that easy. I mean, a computer can handle it really quickly, right? Like, that's the point. What's the dimension of this Jacobian? Well, what is it doing? It's keeping track of the derivative of each of these outputs with respect to each of these inputs. Okay? So there's 4096 outputs, there's 4096 inputs. What's that matrix keeping track of each partial derivative of an output with respect to an input?
4096.
Yeah, ends up being a square matrix, 4096 by 4096. What will this? Oh yeah, first of all, I better answer that question. Yes, 4096 by 4096. Be brave. Who doesn't see that? Who doesn't understand that? Yeah.
What's is that the exclamation mark? Is that the
Oh yeah, that's don't let that throw you off. This is not your factorial. This is just like, wow, that's big. It is really big, actually, if you think about it. Like, that's a lot of, like, those are all float 32s. That's a lot of memory just for that one operation. Fortunately, this is like a really sparse matrix. What's the general like shape of that matrix? Yeah, it's a diagonal matrix. Why is it a diagonal matrix?
Because it maps one to each edge.
Yeah, the fact this is element-wise, and it's just max of the input with a constant, just means that at any one of these, let's say that we're looking at x 100, right? The 100th out of the 4,096 dimensions. The output only depends on that 100th input, right? So that 100th output only depends on the 100th input. So there will be a value there that isn't necessarily 0, and then everything else, all of these other outputs will be split. So x90 or the output, the 99th output, the 98th output, the 1000th output, whatever. Its partial derivative with respect to the 100th input, they're all 0 because that those outputs don't depend on 100th input. So you do have a diagonal matrix, but it's even stronger. We can say something even stronger. What are the possible elements along the diagonal, or like what are the possible entries along the diagonal? Somebody's trying to say it.
1 and
Good,
0.
good. 1 and 0, exactly. It's 1 if the input is greater than 0, right? Because we have basically x, partial of x with respect to x itself. So that gives you 1. But if x is less than 0, then you have 0, partial of 0 with respect to x, which is 0. So it's either a 1 or a 0. So you have a very simple, and you might, at first, until you run into your first memory issues, represent that whole huge matrix, with a bunch of 1s and 0s, but then you'd say that was dumb, because most everything is 0s. I don't need to keep track of all those. I'll just keep track of the diagonal elements, which ones are 0s and which ones are 1s. Okay, cool, good. Let's see, I'm trying to remember. Oh yeah, we were talking about this. Oh yeah, this gets worse. This gets worse. So remember how we're doing mini batch. We're doing stochastic gradient descent. So we sample this mini batch, right? So remember that we're computing this loss for each of the data points in our mini batch. So like, let's say if we have a mini batch of size 100, then this is actually not right. We have 100 of these, 100 times that. Huh, I actually never noticed that before. That's funny. Anyways, so you actually have 100 of these. So you have this huge 4096 by 4096 matrix. So, somewhere on the order of 10 million entries, and then you have 100 of those for each of those points. So that's a lot of storage. What about sorry, we already answered these questions, but let's talk about this. What's the size of this right here? The gradient of the loss with respect to f, which is that. Think of that as like the output variables here. What does that look like? What kind of object is that? The loss, remember, is a one-dimensional or a scalar function. We've got a one-dimensional output. So what does that look like? Yeah, so it's a vector. So you have a single output, the loss, it's a scalar, and then all the partials of that with respect to each one of the outputs, right? So that's going to give you a vector of length 4096, and so the question is, is it a column matrix or is it a row matrix? Like, do I do all these things the right way? Like the kind of flippant answer is, really it's up to you how you decide to keep track of where what columns are and what rows are, and just make sure that you match those up with your gradients. The way it's written here, this should be a column vector of length 4096, and even though these are the same, the same dimension, 4096 by 4096, what should each row of this Jacobian look like? Should it be all the partials of an entry of x, so all the partials of an entry of f with respect to like all the inputs, or vice versa, all the outputs of f with respect to one of the inputs? if this is a column vector, what should it be? Basically, should the f's be in the numerator or in the denominator? They're tricky questions.
Could you repeat your question?
Let's say that we call this a column vector. So this is, we have a scalar loss. It's a vector of all the partials with respect to each of the 4096 outputs of f, right? So what should f look like? Basically, like, what should the rows of f look like? Should it be a single output of f with respect to, so like, it's going to be all the partials of f with respect to all the inputs of x, or each of the entries of x, or vice versa? Should it be a single entry of x and its partials, the partials of f with respect to all of those x's? Which one should it be? Say it again.
All of the F's should be the row.
All of the f's?
A single input and all the outputs.
Okay, single input and all the outputs. Why do you say that?
So it cancels with the column, because those are all the outputs of the denominator.
Yeah, so think of this as a dot product, right? It's going to be like a dot product of two things. And that dot product ought to be something where, like, these things sort of cancel out, right? So what we're left with is this thing right here. So what's the size of this going to be? Partial of L with respect to x. What will that be? It's a vector of dimension 4096. How many entries does it have? Well, sorry, sorry, I said that wrong. Is it a row vector or a column vector? It's a column vector, right? Okay, so this is going to be some matrix, and to get it so that there's a kind of cancellation, it should be all of the entries of f with respect to one. The row should be all of the entries of f with respect to the partials with respect to one of the values of x. Does that make sense? So what does that mean? Like, the f's go along which way? The rows or the columns? The indices of f go along the rows or the columns? They go along the columns, and the x's give you the rows. Yeah. Linear algebra sucks for this reason, you know? It's just like, it's all about keeping track of indices. That's seriously, if you can like get to that point, and you can just look at your linear algebra teacher and just say like, it's just all about keeping track of indices, dude. Then you're there. You've made it. Because then you can just kind of make it up yourself as long as everything matches. What was the question?
So I'm just trying to summarize what you said, and I want to know if it's a correct summary. So DLDF is a column vector of F1 through 4096. So then each row should also have F1 through 4096.
Exactly.
Okay.
Good. That's right. And that means that the partials with respect to x, it's the same x all the way through that row. It's like, x 100 or x 1000 or whatever. Right. Good. So the row indices give you which x you're using, and the column indices give you which f you're using. Good. That was fun, wasn't it? Linear algebra. Really, linear algebra and a little bit of calculus kind of run the world. And this is it. It's all right here. Back propagation. All right. So vectorized example here to kind of finish out the lecture today. So RF here is still a vector value, or sorry, is a scalar valued function, and it's going to be the square of the magnitude of our product of w and x. Okay? So the way that looks is we take each of the individual entries in the resulting vector, and we square them. We add them all together, and that gives us the square of the magnitude, or the Euclidean magnitude. To get the magnitude, we would just take the square root of that. So so the question is, how do we do all of this when we're in a vectorized, or when we have like vectorized inputs, right? So, in this case, we're going to let W be a square matrix n by n. We're going to let X be a column vector of dimension n. This is the computation graph. We do a matrix vector multiplication, and then we apply this L2 operation. So this has to do with just some mathematical definitions of what these spaces are like, but the idea is that we're just doing this thing right here. So after we get the product and this becomes a vector, we're gonna do this operation here. So can you do the same kinds of things, but just now keep track of all of the values along the way? And the answer is yes. You're going to pick some values for W. You're going to pick some values for X. You are going to have representations for your operations. So this is the output of W times X, that matrix vector product, and this is this node here, the square of the L2 magnitude. We're going to need partials of those with respect to all of the things. First of all, we do our forward pass, W times X. We get our values. Now we want to do the backwards pass. So again, this is a scalar value. We always we initialize this with our downstream gradient being 1. Now the question is, what's going to go here? So what we need is our gradients. So if we look at this operation right here, we have we're going to want to compute the partials of f with respect to each of the inputs of q, right? And if we do that, here we see we get, these are all just quadratic terms with respect to each q. That's an easy derivative to take. So we just get 2 times the input. And if we think about this as a vector, so like the full gradient, we can see that this is just 2 times q, right? So this has a fairly simple, the gradient of f with respect to the input vector q is just 2 times that input vector. It's actually very simple. And this in general is the way to work this kind of stuff out when you're wondering what to do. If you don't know like how to do the vector calculus, you just look at each of the individual entries there, work those out, and then usually there's a simple way to kind of see like, oh, I see, that's actually, I can write that in vector notation very simply. Okay, so I've got that. So I've got my gradient of f with respect to my inputs q. This is that f here. It's kind of unfortunate to reuse f again. I'm sorry, but that's this operation here. So I have my inputs q right here. I have my local gradient, so I'm going to have 2 times that. And then I have my downstream gradient, 1, I'm going to multiply that with. So I should just have 2 times q times 1, and that's what I get here as as now the new downstream gradient to propagate upstream. Now I have to deal with this w times x. Really not that big of a deal. So the output q, right, is just this product. It's a vector. So if I look at each one of those entries, I can think about how does the different entries of my matrix W, how does that output change with respect to that? So let's think about this. So in this simple example of just 2 by 2, let's think about Q1. How does Q1 change with respect to each of the entries of W? Well, remember that each one of these is just, think of this as like the dot product of the row with the vector x. So if this is Q1, then whenever W is in row 1, we expect for there to be something like some kind of contribution to that gradient. But if we're in a different row than Q1, then we don't expect there to be any contribution from these entries here, right? So only the parameters in the first row contribute to Q1, only the parameters in the second row contribute to Q2, and so forth, right? And what we're trying to do is indicate that here. This right here is kind of a mathematical notation that says this is a 1 if this condition holds, if the index Q here, so this would correspond to one of these rows, is equal to the index I. So we're considering the kth row of W. This would be a 1, and it's 0 otherwise. This has names like delta function or something like that, but this is like the indicator, like an indicator variable. It's 1 when the condition holds, and 0 otherwise. So it's 1 just when we're considering the kth row of W. So again, let's think about Q1. We're going to think about what is the contribution to that particle, the full gradient, for each of these entries of W in the first row. Well, this is really simple, right? This is just a bunch of linear terms. So if I think about what is the partial with respect to W11, the entry in the first row and first column, then it's just going to be x1. So the entry in the first row of x. And that's what we have here. We have, so only for that first row is this going to be a 1. So just imagine that's set to 1. So let's just set k equal to 1, y equal to 1. As we work our way through the columns here of W, which correspond to the rows of x, I'm just going to get, I take the partial with respect to this parameter, I'm just going to get x1. Take the partial with respect to W1, comma 2, I'm just going to get x2, and so forth, until I get to column n. I'm just going to get n here. So this complicated formula right here just says, this is just going to be the entries of x as I move along as I move from x from the first row to the last row. So this is a compact way of writing down what is the gradient of each of Q1, Q2, Qn with respect to the entries of W. It looks complicated, but it's very, very simple. This picks out the row that you should be on. This picks out the value of x corresponding to the column that you're in, the column of W. Make sense? Again, it's just all like, just keeping track of indices. It's just like, it may seem complicated, but these are all just ways of keeping track of indices. So how do we now think about this with respect to like putting these operations all together? The upstream gradient with the downstream. Well, we're just going to multiply them together, right? We have a bunch of, remember we did this last time, there's a bunch of paths through F to the parameters of W through all of the Q's. So we have to sum up, we have this chain rule for each of these variables, each of the entries of Q, the output of W times X. So we can do this math fairly simply. We know what this is right here. We already computed it. That was a 2 times QK. And then we have this entry as well. We know it's the indicator. Make sure we pick out the right row. And then we just get the value of x corresponding to the right column. And if we put all that together, this term right here is just going to be 0 unless k is equal to I. And so all of these contributions will be 0 except for when k is equal to I. So we get just 2qi, and then the corresponding value at that point, which is xj. So this is the partial of the full output with respect to the input. That's kind of a pain to work through all of that, but all we've done is keep track of the indices all the way and apply our formula. And if we do all that, we can calculate our gradients with respect to W just by plugging in all these values. And you can check that, you know, you can check that on your own. Also, here is an expression of this right here. This is the, you know, all the partials of f with respect to the entries of w. But if we write that down now in like in a vectorized format, it just looks like this. Partial of the gradient of f with respect to q, the gradient of q with respect to w. Yes, always check. Yeah, we can do this math the other way around. Okay, so just with a couple minutes left, all this seems really horrible, right? It is. Like, this is a lot of stuff to keep track of. It's terrible. It's no fun. No one wants to get a PhD in like doing this. So the good news is the reason why we're doing all this is that it's an algorithm, and we just get computers to do all of this. Essentially, all of your frameworks for doing deep learning look like this. They have you know, like in Python, they have a bunch of classes for all the different kinds of operations you could have, and they have a definition for the forward pass of that operation and a definition for the backward pass of that operation. And then automatic differentiation connects all those up through backpropagation algorithm to allow you to compute these really complex gradients. And that's the good news. So in homework 1, you're going to be doing a lot of this on your own for simple operations. But then as you get into homework 2, you'll switch over to using PyTorch, and that's the whole point of PyTorch or TensorFlow or JAX or other frameworks that you have used or come in contact with or will learn about in the future or will be written, is to basically provide all these definitions for you, so all you're doing is just the fun coding of saying, you know, here's what my network looks like. And you just define that, and all the other stuff kind of comes for free. Right, you're going to do this in your homework. So that's it. Here's a summary of what we've done so far. And yeah.